Ontario has been of a close-knit community of teachers who really care about their practice and who are very conscientious about what they do. And it's just been a pleasure to be a part of. So I've known about ECOO for a few years now. This is my first time being here, and the organizers have been very generous and welcoming. So thanks for having me here. The name of my session is What's Happening Here? A Sense-Making Approach to Coding. And before I begin, as Alana says, I want to acknowledge that Code Jeunesse and I personally are headquartered, you might say, on unceded Indigenous lands. So we know the traditional custodians of these lands as the Mohawk, but they call themselves Ganyengahaga. And I personally am based in Montreal, as well as KCJ normally, and they call Montreal Jojaga. So right now I'm outside the city, which is why you see a fireplace behind me. I'm joining from vacation with the family. So I'm well positioned under our Wi-Fi router. My kids know to turn off Netflix for the next little while. So fingers crossed, I think we're not going to have any technical problems. We'll be here together for 45 minutes. I'm the Director of Education R&D for Code Jeunesse, and we call ourselves KCJ for short. It's a bilingual name, Kids Code and Code Jeunesse. And we're headquartered in Montreal, as I said, but we have presence across the country. So I come to KCJ after several years of volunteering with the organization while I was working in the software and IT world. I started both as a parent and a volunteer and sort of got bitten by the bug teaching for KCJ. I volunteered and they would send me into schools to do after school programming. I joined the team first on the oversight committee and then developing lesson plans. And ultimately, when KCJ scaled up, thanks to CanCode, I left my former career path and came full-time into computer science education. So I have this directorship at KCJ, and I'm also working on a master's degree in math and computer science education at McGill. So I welcome everybody to get in touch with me if you ever want to. I'm just Mike at kidscodejeunesse.org, all one word. And you'll find me on Twitter. I'm connected to lots of people here already. I'd love to meet more of you. I'm at mdeutschmtl. So a little bit about KCJ. So I imagine many or all of you were in Juliette Waters' opening keynote just in the last hour, but KCJ is a nationwide bilingual charity. Our mission is to give every Canadian child access to digital skills education, and we try to do that in as many different ways as we can. We reach into communities through code clubs, which are often in public libraries. We also do weekend activities for families, and we do festivals and things like that. And of course, we come into schools and we work with teachers and with students. I just want to say in brief, you may have seen Matt Griffin in his KCJ presentation, I believe that was yesterday, talking about the new math curriculum. But we have quite a footprint in Ontario. So of course in the Greater Toronto area and in Ottawa, but we also have people in Kitchener-Waterloo. And we've done road trips far north and far west. And so in the last couple of school years, these are just a sampling of the places where we've reached. I myself, back this February, gave a talk similar to this at ACE, the Association of Computing Science Educators. And since, of course, COVID hit, we did a pivot, and we had started already to start teaching online, doing our workshops direct to classrooms online through webinars. And now, of course, we're doing our professional development, our teacher training fully online as well. And we reach directly into living rooms across Canada through code clubs and other activities in the spring and summer. So you may have seen us at these other places. And a little bit about KCJ and our audience and our approach to teaching. So there are, of course, many organizations and many individual teachers getting into teaching coding. This is, as it was said earlier this morning, not anything completely new, although there is certainly a wave that's been building up in the last 10 years. Our primary audience and who we really aim ourselves at are middle grade generalist teachers, that is to say grade 3 to 8, and we also say generalist students. We're looking to help people who are starting to use coding for all kinds of purposes, and Juliette alluded to this in her talk. We don't tend to get very deep into robotics and hands-on STEM and making and things like that. We are really specialists at the first step or two into coding for people who might use computational thinking and coding for STEM purposes, but who also might use it for the arts or social sciences or any other avenue that they pursue. Our teaching approach, as I allude to in the name of this session, we try to teach coding in a way that supports sense-making, self-efficacy, and positive affect. And there's a bit of a challenge to do that in just a 1 or 2 hour introductory meeting when we walk into a classroom or encounter teachers that we've never known before. And this pushes us to structure our lessons, our resources, and the way that we facilitate in such a way that we support sense-making. So here's the first time, I haven't really even gotten into it yet, but I just want to pause. And in the chat window, if there's anybody here who has experience with that term sense-making, I'd like to know, what does that make you think of? Is this a term that you're familiar with? I know it's making the rounds, particularly in math education and somewhat in science, and I'm curious to know the makeup of the group here. Do we have people that are familiar with sense-making? If so, say so in the chat and elaborate for just a sentence if you wouldn't mind. And Elena, I'll ask you to read those because I don't have visibility on that right now.
So our first comment is from Wendy Fisher, and she says in the arts is where she sees sense making.
Oh, interesting. Wendy, can I allow you to open your mic and say a little more about that? Or you can chat.
Wendy says making sense through interpretation.
Yeah. I like that. That's definitely parallel to what we have going on. Yeah, you have your mic on?
As students watch each other's projects, particularly in dance or nonverbal forms of drama, there's a lot of sense making happening.
Oh, that's so cool. Okay, we actually have someone on our team who said something similar, and you're the first teacher that I've said that I've heard make that connection. I'm glad you did. Do we have maybe one other person who's mentioned sense making in the chat?
No responses so far.
No. Okay. Well, then I'll spill the beans. So this is our take on sense making, and I have one toe in the education research world through my master's program, and I'm trying to bring good recent research into Kids Code Jeunesse to inform how we do our teaching and how we design our materials. So this is a paper just from a year ago, Fitzgerald and Palanchar. The way they define sense making is almost by example. They say sense making is a way that people develop conceptual understanding of something new that they face for the first time. In the realm of education, sense making is often opposed to answer getting, which you may or may not heard of in those terms, but I think we understand colloquially what that means. Answer getting is an approach to teaching where students develop procedural competence, that is, they can follow algorithms that we instruct them in, but that tends to result in very narrow strategies that they have in their tool set and a rather inflexible way in which they're able to deploy those strategies. The question students often ask themselves is, when they hand in a sheet that was done in an answer getting approach, did I do it right? Or they may be asking themselves, or they may be asking their peers or the teacher, did I do it right? And sense making, on the other hand, is when a teacher deliberately structures their teaching to develop conceptual understanding, to provide multiple strategies, and to give students the tools that they need to apply them flexibly and creatively. And the key question that a student might ask themselves here is, does this make sense? The task I'm being given, the question I'm being asked. And Fitzgerald and Palanchar make a very key point here when they say that sense making is social. And Wendy, if I got your name right, that's really resonates with what you just told us. Sense making is social. And I also want to flag something that Mavis Dixon, our director of programs, just said internally a week ago. She said what she really found out of this approach is it teaches students and teachers to learn to see and to ask questions. right? It's about finding mental connections between things you already know and something new that you're approaching for the first time. And I'll tie this to something that's in the talk description. I mentioned in the description that we have standard instructional routines. That may also be a keyword that some of you know, instructional routines. There is a very classic computer science way of teaching, which is the follow me. And what you see here in this screenshot is from a Code Club activity. So Code Club is under the Kids Code Jeunesse umbrella. There are, I think, 1,000 independently volunteer-run code clubs around Canada. And that comes with all these resources, including ones that you see here. And what that often looks like is a self-paced or even a facilitated step-by-step building of a project. And what we find is when we go into a classroom or we run an activity with kids on the weekends or an enrichment activity, we can do a step-by-step and we can improve it with good facilitation technique by coding live up on the board, maybe by intentionally or even unintentionally making mistakes so that students can watch us, the professionals, fumble around and tinker until we get things working the way we do. But fundamentally, the step-by-step follow me approach has its limitations. And I think that probably feels familiar to you as teachers. When you allow students to navigate step-by-step at their own pace or even following you, inevitably some students are going to absorb this at a faster pace and others at a slower pace. And what you end up with is a very uneven sense of accomplishment at the end. And this is something that we've noticed. And when we do our introductory lessons, sometimes if we get a full school year, 1,000 or 2,000 across the country, this is a pattern that we've identified. So there's this other instructional routine that's common in teaching coding, which is take this, something that I've pre-built partially or fully, and remix it, right? Remixing is a term that's become very common with the advent of Scratch, because the people who built Scratch, as Juliet said before, are from MIT, and one of the features that they built in very deliberately was a remix button, so that everyone who shares a project shares their source code to the Scratch community. So somebody who's coming along and views another person's project that's been shared can see how they did it, and then furthermore can remix and tweak and change around or extend or debug and make that project their own. Remix is a real key feature of the Scratch ethos. And we do this sometimes, and what you see here is from the Ottawa Catholic School Board. I don't know who exactly this is. They identified themselves in their Scratch username as the OCSB coders. I would guess they came to a KCJ PD event because this is a project that I recognize. Our team built this. And what we've done is we've given teachers a starter project, which is a map of the world, color-coded by continent. And this is a very flexible starting point for building all kinds of curricular-based activities. We've started you off with an airplane and some comments in the code area that point you in directions where you might want to take this. So that's a second common instructional routine. And where we started to branch out in the last year and a half is we've started to invert this process. Ordinarily in those first two, students don't know where we're going, right? They don't know what the final product is going to look like. And we've discovered that robs them of a certain amount of understanding that would help them scaffold themselves towards building the finished thing. So what we've started is we invert this process now. We start with a completed demo with a very carefully designed instructional routine around it. And then the third element, those are the first two things that you see here, a Scratch project and then an instructional routine at the top. And then at the bottom, we've supplemented that with a worksheet that we sometimes use. And really, we spend time on this before anybody opens up their computers and starts to code. And we ask students to consider, okay, look at this program. It's a finished product that I built. What do you think this program might be doing on the inside that's making it achieve the effect that we all see on the outside? In other words, we're all in this together. I built something, and I'm telling you that very clearly, so this doesn't feel like magic. This is something that I had to figure out, I managed to build this thing. And implicit in that is you could too. I can show you. But together we start to grapple with it from the outside before we ever see what's on the inside. So I've already used up 18 minutes here, but this is a run through of what we're going to do in the remaining time we have together. We're going to try this instructional routine that I just mentioned. I'm going to talk briefly about the ideas and the intent behind it. And we'll finish up by where we think you might find this useful in your classroom. Okay, let me pause here. Are there any questions in the chat? Anybody want to add a comment to what you've seen so far? Or have a question that we should talk about before we move on?
I think this is really resonating with people. No questions at this point.
Okay. We see heads nodding, we see thumbs up. Are there things like that? Or stunned silence at the profundity of it all?
Stunned silence.
Okay. This is, when we do this as a live PD session, obviously it's very, very interactive. So we've lost a little bit something here.
Carol, Ann, and Wendy both say that they are waiting and they're excited and it's all good. So.
Okay, great. Okay, so here we are. I've blown up the image of that Scratch project that we saw in the last slide. I'm going to start to ask you what's going on inside. I've mentioned this is an instructional routine. Those of you who've had PD in math pedagogy, math teaching, instructional routine may mean something to you. That may be queuing up something in your brain. I'm going to do a what do you notice, what do you wonder? So let me leave my presentation. I'm going to go over to the Scratch maze itself. Can everybody see that? I'm still sharing that.
Yes, it looks good.
Okay, so I'm going to click the green flag because we all know in Scratch that's how you begin a program. Oh, and just right off the bat, something just happened. I'm going to ask everyone, fingers on keyboards, start to enter into the chat. What do you notice? And I mean it as simply as I just said it. What do you see in front of you? No trickery here. I'm not looking for a brilliant answer. Very, very simply, what do you see? And Alana, can I ask you to read me a comment or two?
You got it. So there's two options. People are seeing instructions, two red rectangles, buttons. The picture changed, pixelated fonts.
Excellent. I like all of those things. So I heard two red rectangles and I heard buttons. I'd like to know more about that. What suggests, to the person who said buttons, what suggests that these are buttons?
This is Carol Ann Aubrey, who also identifies as your OCSB coder person.
Hey, Carol Ann, it's nice to meet you.
Carol Ann, do you want to jump in?
I guess I know they are buttons because I've played lots of games and that's what they look like to me. They're big and red and look like they should be pushed.
I
have an
agree with
outline around them.
I agree with you. So I'm going to do that. Now, rather than showing you how to play, the object of this little routine here is that through me, you're going to drive me as your avatar, and together we're going to figure out how to play. So I'm not going to cut to those instructions, but I'm going to click on Start. Again, I'm going to ask everyone, what do you notice? Fingers again on the chat. Just start piling in. What do you notice? And Alana, you can read them out as you go.
There's a time, multiple pathways, a map, timer, a maze. Timer's going fast.
That timer is going fast. Does anybody notice that we have a character that we can play?
Also, no, the character didn't come up. Also, there is a start and there is an end.
There's a start and there's an end. Okay, that's a really interesting inference. So there's a maze or a map.
Sorry, there's a little red person in the corner.
Little red person in the corner. So I'm assuming we understand this now. There's a map. I have a character. That character needs to do something. So I pivot to my next question. You've told me what you notice. What are you wondering? Folks, what are you wondering? And underneath that is, what would you like me to try? Since you can't interact with this.
Angie wants to know what's the purple square and how to get from one place to another, says Carol Ann. If
Does
you use the
anybody have an
cursor,
idea?
yeah. So many wonderings. I wonder which pathway to take, how to move the character, how do you score? And if you use the cursor arrows, will the character move?
Oh, well, that's something I can act on right there. If I use the cursor arrows, oh yeah, look, my little character moves. Okay.
Another question is, if there seems to be breaks in the path, but do we have to stay on the path? Like, I think, can we cross the blue line?
Well, somebody is wondering, I'll rephrase what you just wondered. What happens if I cross the blue line? So suppose I assume that green is the goal. I think somebody inferred that. Oh, did anybody hear a sound effect there? Is it sharing my audio as well?
It just sort of went blank for a second. R, don't be so hard on yourself. R says, never mind, the path is yellow.
Okay, so the path is yellow, and something happens when I bump into these blue walls. And that's ordinarily, as the teacher, I wouldn't feed that idea of bumping into the blue walls. I would wait to see if a student voiced that. But okay, when I bump into the blue walls, what seems to happen? And I'll start to make my way through here. What seems to happen? What do you notice happens when I bump into those blue walls? I'll just feed it. Right?
Oh, your score goes down.
Oh, my score goes down, and it sends me back to the beginning.
Yes.
Look at that, and I can repeat that as many times as I want. It seems to do the same thing every time. Oh, wait a minute.
You start back at the start every time you bump into a wall. What do you mean you lost? That's depressing.
Okay, more noticings. The timer has stopped. My score is -10, and I have lost.
Heather says that's brutal.
It is brutal, totally brutal. So let's do this.
And also that your score is negative, and -10 means lost. Is that the question? Yes.
Well, should we experiment a little?
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. Okay, we seem to have discovered something here together. -10 seems to be the condition where you lose. So I'll start this one more time. Anybody else wondering anything that they'd like me to try?
The timer is going up, wondering if time doesn't really matter.
We did reach 160 or something like that last time. And that didn't seem to limit me.
Also, what happens when you touch the purple square?
Okay. What happens when I touch the purple square? That's a good wondering. Oh, I heard a sound effect. It sounded like a laser sound.
And
what did that do?
Also, how do you get to a next level? And then someone said, whoa, a portal. A portal!
Many portal? Well, in order to validate that hypothesis, I'm going to have to try it again. Ready? Oh, that time it sent me back to the beginning. I'm going to try it a third time and see if there's a pattern to this or not, and then we'll move on. Okay, pattern, we think?
Pattern, but now I'm wondering what happens if we get all the way to the green one? Will it send us back to the purple one?
Mm-hmm. Ready, set, go. Oh.
Level 2.
Level 2. Okay, so in the interest of time, I'm not going to complete this level. There's no new obstacles here. I'll ask you to notice. We've got a green square, which I'm going to assume does the same thing as it did the first time around. And we've got 2 purple squares. And we have a maze that seems a little trickier to get around. So, okay, I'm going to stop here. This was a really nice notice wonder. I don't see the chat, but Alana, from what you're reading me, people are picking out slightly different things from one another, which is exactly what we hope is going to happen. So now let me ask again, has anyone here done a routine like this in their class? And if so, which subject was it in?
There are a lot of woohoos. People are really liking this idea. Nothing in response to that current question yet, but
okay.
A wondering again of, are we taking a chance when we dive into the purple square? Is this about integers?
Oh, are we taking a chance? Whoever that is, would you like to elaborate on that a little?
That was R. R, do you want to grab the mic?
Yeah, I think when you go to the purple square, it's always unpredictable. It'll send you to an unknown place, I think.
Yeah, thank you for saying so. I'm going to reset the game and I'm going to try just one more time. We've now done this 3 times. I'm going to do it a 4th. Seem random?
R says yes, it seems random. It's about probability.
Yeah, I'll confirm for you. It's random. Yeah. So
a couple other questions. Sorry, someone wants to know, does this have to do with visual arts, deconstruction, and artwork? It's another sense-making connection.
Yeah, that's a terrific connection. Deconstruction, well, if you bring that into the world of computing and coding and computational thinking, what is deconstruction often called? Juliet mentioned it in her keynote this morning. There are a number of definitions of computational thinking. Right? Computational thinking is what happens inside our minds when we approach something and we either try to understand something digital that was built as software or an app or code, and we try to either understand it or we sit down and try to build something. It's the in-between from the computer to our idea is computational thinking.
2 ideas on that one. Sorry, Mike. One person said decomposing and the other person said tinkering.
Exactly. So I'm going to go with decomposing to answer that specific question, right? Deconstruction in the art world and decomposing in the computer world. And there are, shades of subtle difference, but they're essentially talking about the same thing. So that was the routine. I now want to just show you quickly the worksheet that we pair with this. So from this introductory demo that our team started to sense was useful, we started doing this in practice. It was our instructor, Meggie, was the first one, Meggie Carrier. She's based in Montreal with us. She was the first one that I saw ever do this spontaneously. And I thought this was really interesting, just opening with a demo of the thing you were all about to build together. We started digging in and saying, okay, well, we could ask the notice and wonder question, but that's going to give us a very scattered set of answers. How do we start to bring order to that from all of those different notices and wonders into usable parts that students can start constructively building with? Because if you've got some coding experience, you may have experienced that there's this whole vocabulary in Scratch or in microbits or in any other platform. It's usually given to you, the programmer, on the left-hand side. That seems to be the convention these days. You have the full vocabulary of blocks, when you're block programming, that you have at your disposal, courtesy of the people who built the platform. Again, people behind the scenes. And you get to drag and drop these into your workspace. And you sort of, as a student, you get to know the vocabulary that you have to work with. It's in computing terms, Seymour Papert and others used to talk about this as a grammar, right? There is syntax, there is grammar, there is a vocabulary. But these are very, very low-level building blocks. These are akin to the individual Lego bricks. But if you were trying to build something complex, a working Lego creation, it's not enough to know your vocabulary of bricks. You need to understand the sub-assemblies, how a gear works together with an axle, with a wheel, or maybe how you can stack up small bricks into a tall tower. And so whenever you find a situation that calls for a tall, skinny tower, you have that pattern in your head, and you know that that's something you can reach into your Legos and build to solve whatever need you have right at the moment. So this worksheet is our attempt to do that with block code. We've also started tinkering with a version for text programming if students are learning Python or processing or JavaScript or other languages that are now commonly used in middle grades and secondary high school. But this is the one that we're proposing for block coding, and we've been playing with this since February. We unveiled it in our first few workshops in schools at the very tail end of February, and then the first 2 weeks of March before everything fell to pieces. We had good traction with it in the very early days, but we sort of been in a holding pattern, and that's why I'm happy to be bringing it back to this audience. And we hope that you'll find this useful and use it on your own. I notice I'm now down to 13 minutes, so I got to get moving. This mostly comes from my brain, and I've been workshopping it with the team at KCJ, with our instructional team, and with our R&D team, my team. And what we've tried to do is separate out 6 different types of mechanisms that are often used in block coding programs. Elements like characters, moving parts, and other entities. And you'll see examples of what that might mean. Triggers and inputs, in other words, things that make other things happen. A program either taking some kind of signal from its user or from sensors or detecting things. Information and data. What does a program need to record or remember as it goes along? This is, it's not something that I find is talked about very much, but when I was young learning programming, we talked a lot about computer memory. We talked a lot about what was happening in the guts of the computer, and memory was one of them. And I think that's a very useful metaphor. So we talk about that here. Starting and restarting at the bottom left here. What does the program need to do at the beginning or to start over? Then changing conditions. Does this program need to know what to do in certain situations? Go option A or option B? Does it need to have multiple outcomes? Are there problems that might arise that it needs to safeguard against? If you're building a chatbot, for example, do you need to know which answers are valid from your user and which ones are not? And then lastly, display and output. What does this program need to show or give back to us, the user? That could be sound, images, etc. So I first experimented with my own kids at home, and this is what it looked like with my 16-year-old when she did this, with exactly this project. And then we did it digitally with a focus group on a shared whiteboard, and I'm really hoping that we can get to this before we close today. We're going to do this together. And so now my question to you is, having done this notice and wonder, do you think you could reproduce this or parts of this? I'll take 1 or 2 people who have a feeling on that.
Ian says this is an amazing, helpful discussion framework.
Cool. I'll go ahead one more. If you've got a little bit of Scratch experience, I'm going to ask you, how did I make the blue walls?
So my thought about making the blue walls is you drew a background that had blocks or rectangles in it that made the shape of the blue walls on top of the yellow.
Mm-hmm. So there's a painting tool in Scratch, and these are shapes that I made. That is one way I could have done that.
Diane is wondering if you used some sort of sensing button, a sensing block.
Mm-hmm. That answers my second question. How did I do the bumping into things? Yep, there are sensing blocks. So just to tie up that first one, there are multiple ways I could have done those blue walls, right? Scratch and every other programming language gives you multiple ways to do things. And that's one of the tricky things as a teacher. When you start to teach coding, especially if you're new and you haven't mastered the entire tool set yourself, it can be overwhelming to think of, oh my God, I need to know all the different ways to do things. Well, as Julia said, you don't need to have all the answers. This is something that we can all tinker with together. But I'll just say there are at least 2 ways that I could have done those blue walls. So one is, as a backdrop using the paint tools, I could have made blue rectangles. I could have used a blue paintbrush to set those up. Or, in fact, because of the way Scratch works, those could be moving parts themselves. Those could be sprites. Those could be characters that happen to have a shape of a blue rectangle or sideways rectangle, right? And whenever you make an entity like that, a sprite, you can give it code. So the code for bumping into things and detecting those collisions could reside in our red little character, or could reside in the walls themselves, or in the backdrop. How did I detect you lose? Does anybody remember how that went?
Just kind of going back in the chat a little bit, someone said, is it an if then block, or if I hit the blue move back to the beginning. Diane is wondering, is when counter equals -10?
Mm-hmm.
And that the code for the sound might be in the wall sprites is what Carol Ann is wondering?
Yeah, it definitely could be, right? At any time, whichever code is doing the collision detecting, it's going to, when it detects a collision, it's going to run through a series of steps. One is it's going to tell that sprite to go back to the beginning. A second is it's going to make a sound. And a third is it's going to change your score. All right, those I think are the three things that I remember it was doing. So yes. And detecting you lose was just listening to that score, right? So that score is something that the program needs to remember or keep track of. I'll end with this question for now. What do you think was different about this routine from a follow me approach? I could have said, okay, everyone, open up your laptops, start a new Scratch project, log into your account, take this sprite, and now paint this, and now paint this, and do this code, and this code, and this code, and you could have followed me. Some of you might have completed it. What was different about this approach?
Diana says, notice and wonder allows students to discover that there are different ways to accomplish the same thing. And Carol Ann says, it was more fun.
Oh, I'm glad you thought so. And yes, yes to both.
Heather says it's stimulating and engaging, and Wendy says it's more difficult to invite multiple strategies.
When you do it the old way. I like that. I agree. So I've only got a few minutes left. I'm going to zip through this. Where did this come from? I've sort of alluded to it already. Our audience is novices. So when we walk into a classroom, we have no idea. Even if we've had a conversation with the teacher beforehand for 10 minutes, we really don't know where their students are, what comfort level they have with coding, how many of their students are already accelerated, and how many are just beginning. And starting with a routine like this levels the playing field. We also hear from stakeholders in the STEM world. It could be secondary school teachers, it could be university level teachers, even corporations that we talk to. They say that even among graduates who come out with a computer science degree or a related degree, they see a gap in sense making. That's our terminology. They don't say sense making, but they say there's a gap in problem solving, or a gap in understanding context, or tackling novel problems. And this is very, very important for them. And finally, from my personal experience, this really struck me last school year when my grade 10 daughter here in Montreal was learning Python in her computer science class. I tweeted about it, and it was by far the biggest attention getter that I've ever put on Twitter. And one relevant point that I put here is, in sitting with my daughter, I realized it's hard to straighten out your understanding of a problem and map out how you're going to use the building blocks that you've just learned. I found it distressing to discover how fuzzy it is to say, oh, okay, I get the problem. There's actually quite a lot of work that it takes to get from, okay, I get it, to I understand how I'm going to build it, and I'm ready to get started. So in the routine, the notice and wonder, what's my intent here? We've taken up a lot of time, so I'll just jump to my conclusions here. We want to start the classroom with a level playing field. And because all we're doing is using our eyes and ears and senses, there are multiple avenues of access. Everyone in the classroom is going to notice something a little bit different. And even if there's a cluster of students, or even everybody who notices the same thing, that's fine. There's going to be little interesting subtleties that people pick up, and it may not be the people that you're accustomed to hearing from in a group setting. Another really nice thing that the math educators talk about is this gives us access to everybody else's thinking. Ordinarily, the teacher broadcasts her thinking to the class with direct instruction. So each individual student gets a download of that and has to incorporate that into their mental model. But unless you're doing think, pair, share, or small groups as a real concerted effort, they don't get very much access to their peers' thinking. But in a routine like this with the whole class, they really, really do. And that gives them all a chance to fill in gaps in their understanding, to see things from different angles. And finally, it gives them additional strategies for how they're actually going to build something in code. I'm going to share these slides. I haven't uploaded them yet, but they'll be there. And I give some references here as to the theory of where this comes from. In part, it's from the ambitious pedagogy that comes from the math ed world. And even in computer science, people are starting to talk like this. They call it program comprehension or code comprehension. I've got some links here of math routines that I really, really like and that I'm trying to bring into KCJ. Notice and Wonder is just the first one. Illustrative math, the NCTM, those are both in the States. And David Wees is a really, really very clear writer. He's a blogger in BC. He's a math teacher and he dabbles in code as well. So this worksheet, okay, what's my intent here? And I'm really down to my last 2 minutes. I'm trying to prime students to recognize the sub-assemblies, like I said, like almost in Lego, that we use in programming, that are the level between the individual steps of code and quote unquote things that the program needs to do. When we run right into follow me step by step by step by step, we skip over that completely. Also, as we mentioned, I'm trying to separate out the ideas, what the program's doing, from how they might be carried out, because in a lot of cases, there's multiple ways to do it. And also, you may have noticed here, I'm not queuing up specific blocks. I'm not saying, are there loops or repeats? I'm not saying, well, in the screenshot here, it used to say variables. It no longer does. I'm not saying create a variable. I want to allow students to understand that first before they go. Ultimately, the overall effect is we're doing our computational thinking together, openly, before we start to code. Man, if we had more time, I was going to ask you to give some ECOOCamp shout outs, because I haven't seen any other sessions, and both for my benefit and for the benefit of others who have to pick a track in any given time slot, what else have you seen here that you would connect this to? Because I know KCJ is not the only one doing it. We've met lots of people who have really interesting takes on teaching coding in a style that's like this. If you've got a second, something that jumps to mind, throw it in the chat so everybody can see.
Maybe just while people are talking or thinking about that question, I'm going to go ahead and do some housekeeping. I just popped into our chat an after chat room so that you can join and talk with Mike after our session is finished.
That's great.
Just because we'll need to move quickly into our next session in this room. However, I also would like to take a second and just announce our door prize winners, if that's okay. So we have a Chromebook / iPad license for Comic Life 3 that was donated by Plask. And the winner of that license is Carol Ann Aubrey. So Carol Ann, congratulations. I just need you to maybe pop in the chat an email address, or we'll work out a way for you to contact me after the fact. Also, we have a great book called Create by Bethany Petty, and that's a giveaway door prize, and the winner of that is Diana Mancuso. Congratulations, Diana. If you don't mind, please, again, just leave me a contact email so we can make sure that we get to that. So just looking back at the chat now, Wendy said, someone said encouraging fake code so students can talk about their thinking before they know the vocabulary in unplugged coding. She didn't mention who this someone was.
There's a name for that. Fake code is often called pseudocode. Yep, that's a real thing in the discipline of computer science. Write out what your algorithm is just in simple language before you start coding. And Alana, I just gave you back control.
Thank you. So we've just got I just want to point out what the next session is for people and get you going, because I know that this question period is sort of a bit free flow right now. But I did want to bring up that Wendy said she thinks that they meant students create their own language for describing code.
Oh.
I'm not sure if that resonates. Also,
yes, Wendy, I think that's exactly right. I like that.
Yes, exactly. And thank you. Mike just popped in this link for the worksheet. That's an awesome starting point. Thank you very much for that, Mike. Is there anything that you wanted to mention in terms of how people reach you or reach Kids Code Jeunesse to go further with this?
So we're kidscodejeunesse.org. I'll pop that in the link.
Awesome.
Right, all one word. I'm at Deutsch MTL on Twitter. And I'll stop there. I've got a couple more things to suggest, but we can do that in the separate chat. So we'll clear this room. Thank you, everybody, for participating. This was really, really fun. And I wish we had been face-to-face and we could work the room together. So next time around. But folks at ECOO, Alana, and your team, you've been wonderful. Thanks again.
Yeah, you bet. Great to have you here. Thanks for the session. Was it ever well timed to come right from the keynote to this? We'll have to make sure to do that in the future as well. Thanks everyone
everybody.
for joining today.
Alana, is there a way for me to save the chat?
You know what? I think there is a way that I can sort of copy and paste it. I'm just going to go ahead and stop our recording and see what I can figure out for you. There it is.